Hi to all. How are you students? Welcome to srinivasphysicsclasses. Till now if you not subscribe my channel, share to your friends, like and comment. Today's topic is amperes circuital law and its proof. This is important for the board exam and its applications also very important. And listen very carefully, that is, what is amperes circuital law? Previously we discussed the Biot savart law and its applications. Now I am going to explain the amperes circuital law, its proof and some of its applications. Let us start. First, what is amperes circuital law? Then for that, the amperes circuital law statement is that the line integral of magnetic induction around a closed path is equal to the mu naught times of net current enclosed by that path. This is our question. Line integral of magnetic induction. This is magnetic induction. Its line integral means integration b bar dot dl bar. This is said to be line integral of magnetic induction. For example, if it is like this there, this is called as, if here surface area is there, then that is called as surface integral of magnetic induction or the volume integral of magnetic induction. Here volume is there means the volume integral, surface is there means surface integral, length is there means that is called as said to be line integral. Along the line we are integrating, right? And now this is the line integral of magnetic induction. Integration b bar dot dl bar is said to be line integral of magnetic induction is equal to mu naught times of current enclosed in that path. What is that? I will explain. Okay, let us consider these are the this is a closed path. Okay, and here there are some currents are there, I1, I2, I3, I4, I5. Okay, I1, I2, I3, I4, I5, I6, I7. This is I7. Okay, I7, I8. Like this there are the currents. And now current enclosed in this path, there is a closed path they give. What is the current enclosed in this path? Here I want the magnetic induction. The magnetic induction may be tangential at a particular point. The line integral of magnetic induction, integration b bar dot dl bar. Okay, this is a current carrying wire. The current, how the current will be there? Current carrying wire will be there. This I1, like this star I1 is there means the current carrying wire is perpendicular to the plane of the board and current is entering into the board, and this is like this there means current is coming outward from the board and it is perpendicular to the board. Okay, outward current and inward current. If the wire is like this there, then how you can draw that on the board? That we will draw with dot or cross. Right, just like this the wire is there means then that we can indicate with cross or dot. Cross indicates the inward current carrying wire, and this current carrying wire, the current is entering into the board plane. Okay, and dot indicates the current coming outward from the board. Let us see here, this is a closed path. Okay, according to Biot savart law, line integral of magnetic induction, integration b bar dot dl bar is equal to mu naught times of, mu naught is what? Mu naught is the permeability of free space. You know that one? Permeability of free space. Its value also we know, right? What is its value? Mu naught value is 4 pi into 10 to the power of minus 7. Okay, its value, that one. And now let us see what is the line integral of magnetic induction equal to mu naught times of net current enclosed by the path. Okay, here we have to take the current enclosed in this path only. What is this is the closed path. Inside that we have to take the current, right? Inside how much current is there? I1, I2, I3, I5, I7, I8. This we cannot include because these two currents I4 and I6 are not in the closed path. We are taking the closed path like this. In that closed path that currents are not there. That's why we cannot write as current enclosed as I4 and I6. Let us see what is the current enclosed. One thing we have to find out while finding the one thing we have to note while finding the net current enclosed, that is inward current you have to take as positive, cross you have to take positive, dot you have to take negative. Okay, opposite currents. Then total current what you will get, I1 positive, this is dot negative, I1 minus I2 plus I3, okay, minus I5 plus I7 plus I8. This is the current enclosed. Okay, line integral of magnetic induction equal mu naught times of net current enclosed. We not included the I4 and I6. Why? Because they are not in the closed path. Okay. Now I am going to explain the proof of ampere circuital law. Ampere circuital law statement is that line integral of magnetic induction around a closed path is equal to the mu naught times of net current enclosed by that path. The mathematical form is integration b bar dot dl bar equal to mu naught I enclosed. Then how to prove this? This is a current carrying wire, okay? This is a current carrying wire, straight infinite current carrying wire. This is a straight infinite current carrying wire. And from this, at a distance small r, okay, at a distance small r, by taking the small r as radius, I am taking one closed path, okay? I am taking one closed path by taking small r as radius, okay? And look at here very carefully. You have to look at very carefully. This is a closed path, and here this closed path, on the closed path I am taking the small elements. On the closed path I am taking the small element. The small element is dl, and the magnetic induction at here I will take as B. Then at that moment, according to Biot, savart, according to ampere circuital law, what we write it here, okay? And look at here very carefully. According to, I want to prove the ampere circuital law. For that I will take this left side and I will prove it is equal to right side. Then for that, what I have to do, right? I want to find out the integration b bar dot dl bar, right? Integration b bar dot dl bar. What do you write here? Integration b bar dot dl bar. We know a bar dot b bar formula, ab cos theta. Here b dl cos theta we have to write. Okay. But from figure we write. But from figure, b bar parallel to dl bar. B bar parallel to dl bar. That's why we write theta as 0. Okay. B bar is tangential will be there. DL also tangential will be there. And now next we have to continue this, right? And for that we will get, but from figure we are writing the theta as 0. Then integration, line integral of b dl cos 0 we are getting. Here b is a constant at smaller distance. Then b we write outside. Okay. Integration dl we have to write. But what is b at here? B is the magnetic induction due to straight wire at a certain distance smaller. That we know already, right? That formula is what? B formula is, we derived magnetic induction due to infinite straight wire. That is magnetic induction due to infinite straight wire formula is mu naught I by 2 pi r. This we know already. This we substitute here, right? B value. Integration dl is what? Dl is a small element on the closed path, not on the current wire. In the Biot savart law, we are taking the dl is a small element on the current carrying wire. But here in ampere circuital law, dl is what? It is a small element, okay, on the closed path. Okay, small element on the closed path, not on the current carrying wire. This is very important. Okay, integration dl is what? This the dl is the small length on the closed path. Integration dl is the full circle length. The full circle length gives the 2 pi r, right? 2 pi gets cancelled. Here r also cancelled. Then finally what you will get? Then we are getting the nu naught I. Then the proof is almost completed, right? The left side is integration b bar dot dl bar, and the right side is we are getting the nu naught I, right? The line integral of magnetic induction is equal to mu naught times of enclosed current. Okay, this is the proof. It was very simple proof, and this is the statement of the Ampere circuital law, and it is the proof of the Ampere circuital law. Take a screenshot and write the notes. Okay, I am going to explain one application after rubbing this. Okay, I will rub total board, and then after that I will continue with one application. Okay, right. Okay, let us see. Let us go for one application of Ampere circuital law. How we can apply the Ampere circuital law, that I will explain. Okay, and application of Ampere circuital law. First, I am going to apply for one thing, that is magnetic induction due to infinite straight current carrying thin wire. I want to find out the magnetic field or induction due to infinite straight current carrying wire. Already that we derived based on Biot savart law, but I am going to derive the same formula by using Ampere circuital law, right? Then how we can apply the Ampere circuital law? Remember that in order to apply the Biot savart law, this is a current carrying wire. On that we have to take the small element, and here we want to find out the magnetic induction. Means you have to join that point, and its distance is r. Then we have the formula for the magnetic induction, that is nu naught by 4 pi into ideal sin theta by r square. This is the formula for the magnetic induction according to Biot savart law. But what is Ampere's law? Ampere's law is for example, if it is a straight current carrying wire, right? Straight current carrying wire. Then if like this also we can indicate the current carrying wire. This is the current carrying wire, right? But the current carrying wire, the wire is inside. Wire is entering into the wire is perpendicular to the board of the plane, just like the wire is just like my hand. Okay, just like this sketch pen. Okay, it is like this there, the wire, and the current is entering, inward current, this one, right? In this, how the magnetic field will be produces? The current is inward. Current is inward means one direction. Thumb shows, we have to use the right hand thumb rule. Current is inward, then the magnetic field is in clockwise direction. That means around this the magnetic field is like this there. This is the magnetic field due to the current carrying wire, right? And this is the current carrying wire. The current goes upward. Around this, how the magnetic field will be produces? Right? We have to use the right hand thumb rule. In that, thumb shows the direction of the current, and curved fingers indicate the magnetic field. Thumb upward, right hand we have to use. Thumb shows the direction of the current, and curved fingers indicates the magnetic field lines or magnetic field, right? And then thumb shows the upward, then like this it will be there. That means like this. This side, right side entering field will be there, right? Right side field is entering. This side outward. The fingers are entering in the right side, and they are coming out in the left side. Okay, this is for example current carrying wire. The current goes up, right? Then at the moment, then how to find out the direction of the magnetic field? Look at here, the current is upward, means up, thumb should be upward. Okay, current is upward means thumb should be upward, and then curved fingers, this side fingers are entering and this side coming outward. That means when the current is upward, this side field entering and this side field coming outward, right? Inward field and outward field, like that it will be there. And now here this field I want to find out due to the current carrying wire, that is by using Ampere circuital law. At that moment we don't take the small element on the wire. Ampere circuital law is that integration of b bar dot dl bar is equal to nu naught times of I. But we have to take the integration along a closed path. That means around the current carrying wire we have to take one closed path. Where we have to take the closed path? Okay, let us see very carefully. You have to hear, right? And now it was very easy. Once if you understood the difference between the Biot savart law and Ampere circuital law, how we will do, right? In Ampere circuital law, we don't take the small element on the wire. We have to take the small element on the closed path. But in Biot savart law, we have to take the small element on the wire only. This is the major difference. This you should remember. Okay, right? And now here this is the current carrying wire, and I want to find out the magnetic induction due to this current carrying wire at a distance smaller. Here I want to find out this B. I want to find out. I am taking the by smaller I will take as radius, then you can form a closed path. Okay, on the closed path, this red color line is a closed path. Okay, around the wire, on the closed path we are taking the small element, that is dl. Then magnetic induction is B, right? Look at here, the fingers are going inward and field also inward, then dl and B are parallel to each other. Then we write according to Ampere's circuital law. Ampere's circuital law. What we write? What is Ampere's circuital law? Ampere's circuital law is that the line integral of magnetic induction, that is integration B bar dot dl bar, is equal to, we write as nu naught times of enclosed current. Okay, and from figure what we write here? From figure we write one thing, that this field and small element are parallel to each other. Then we write B bar parallel to dl bar. When B bar dl bar parallel to each other, then the angle between them become 0. And one more thing we write, the current enclosed. What you will get the current enclosed in the figure? The current enclosed in the path. In this red color closed path, the current enclosed is I. Then we write I enclosed is I. This we substitute in above equation. Then we will get integration B bar dot dl bar, we write as B dl cos theta, where theta is here 0. Okay, we write theta is 0. A bar dot B bar is AB cos theta, B bar dot BDL cos theta, cos 0, nu naught times of current enclosed. What is the current enclosed? Is only I. Right. B, then we will get as integration BDL is equal to mu naught I. Then B is a constant, we write outside, B integration DL is equal to mu naught I. What is integration DL from the figure? DL is a small element on the loop, but integration DL is the full loop length it will gives. Loop is in the shape of circle, right? That is drawn around the current carrying wire by taking smaller radius. Then integration DL is the full circle length. Full circle length is what? 2 pi r, right? Then 2 pi r is equal to mu naught I. Then from this we will get the B formula, magnetic induction due to infinite straight current carrying wire. Then what you are getting here? From the figure you can tell. From this, just it was very simple, that is B is equal to, we write as mu naught I by 2 pi r, right? Then is magnetic induction due to infinite straight current carrying wire depends upon two factors, that is the B is directly proportional to current and B is inversely proportional to the small r. Okay, this is a thin current carrying wire. This is a thin current carrying wire. Now at a distance smaller, if you want to find out the magnetic induction, then that magnetic induction depends upon the current and distance. But here one thing, if you draw the graph B versus smaller graph, how you will get the B versus smaller graph for the thin wire, right? We will get the graph like this. This is B and this is small r. B inversely proportional to r. That's why when small r increases, then B is decreases. We will get the graph like this, right? Now let us go for next one more application. Okay, and this is the simple application. Okay, you can write the note also, right? While applying Biot-Savart law, okay, while applying Biot-Savart law, small element, okay, dl is taken on wire, but while applying ampere circuital law. Ampere circuital law. Small element taken, small element is taken on what? Taken on loop, okay, or closed path. Loop or closed path. Okay, this you have to remember. Now let us go for one more application. Okay, and this is very important for the board exam. This is very important for the board exam. In the previous 3 marks question, by applying ampere circuital law, derive the magnetic induction due to infinite straight current carrying wire. Okay, and take the screenshot and note the points. Okay, let us go for the one question based on this. Look at here. A long straight wire in horizontal plane carries a current of 50 ampere. Its solution, let us go for the solution. The current carrying is 50 amperes. And that is north to south. The current direction is from north to south. For example, this is north and this is south. The current is north to south. Current is north to south. Okay, and now the current flows from north to south. Let us see, this is the direction of the current. They are asking the something, and now I will tell. The current is 50 amperes. This is a current carrying wire. In that, that is current flows from north to south. The current is 50 amperes. They are asking the question that at a distance 2.5 meters from the wire, they are asking the magnetic induction and magnitude and direction. What is the magnitude and direction? Okay, that is our question. Right. Magnitude, it is very easy to find out. What is the formula for the magnitude? Nu naught I by 2 pi r, infinite straight current carrying wire. A long wire, long means infinite. Infinite wire B formula is nu naught I by 2 pi r. Magnetic induction due to wire at a distance smaller formula is this one. We substitute the values. 4 pi, nu naught is 4.10 power minus 7 into I value is 50 by 2 pi into smaller value is 2.5 meters, right? And this pi will cancel. 2 into 2.5. Okay, we cannot cancel this 2. We can multiply this, and then here we will get as 4 into 10 to the power of minus 7 into 50 by 2 into 2.5 is 5, 5 10 ja. Then finally we are getting the B value as 4 into 10 to the power of minus 6 Tesla. Very simple. But what is the direction? Direction is very important. We have to go for the practical for the direction. What is the practical? Right, look at here. Very carefully you have to hear. Okay? Right. And we have to know the directions first. Let us consider this is east. Okay, my hand showing the east. Back of me, west. East, west. Okay, perpendicular to that. This is what? South. This is north. Then the current flows from where to where? Okay, look at here. East, west, east, west, north, south, east, back west, right side south, left side north. Then the current flows from north to south. Look at here. Current flows from north to south, means this side to this side. Okay, look at here. This is south and this is north. This is east, this is west. We discussed already, right? East, west, north, south. Current flows from north to south. Look at here. For example, this red color is south. Current flows that side. That side. This is a wire. Okay. And what they are asking, magnetic induction. Current is flowing towards south, from north to south. This is north south, means this side east west will be there. This side east, this side west. Then what they are asking, magnetic induction at a distance 2.5 meters east of this wire. Okay, what is the east direction of this wire? This is the north-south direction. The wire is there in the horizontal plane, and at 2.5 meters in the east is this side is there. At 2.5 meter here they are asking to find out the magnetic induction. Here at 2.5 meter distance they are asking to find out the magnetic induction in the east side. Here they are asking the magnetic induction. Very simple. This is a current carrying wire at a distance r, B equal to naught I by 2 pi r formula. But what is the direction? You have to use the right hand thumb rule. Look at here. Then current shows the thumb, okay, and the curled fingers indicates the field, and the field here, here it is inward, okay, look at here, and then here it is upward. That means on the east side the current direction, the field direction is upward, okay. This is east, like this. Thumb shows the field and thumb shows the current, curled finger shows the field. Then the current is right side, this side south side, field is like this circle, but the field this side upward and this side downward, the fingers entering it here, and this side coming out, right, like this. That means this side field is upward. In the east side the field direction is vertically upward. Very simple, okay. And one homework I will give, this you must do, very simple. A long straight wire carries AB long, this is also long straight wire, it carries 35 amperes. What is the magnetic field at 20 centimeters from the wire? You convert this 20 centimeters into meter, and they are asking to find out the magnetic field due to current carrying wire at a distance 20 centimeter, that is also long wire. Then for the long wire, B formula we derived, that we can use the same formula, then we will get the answer. You can write this answer in the comment, okay. Thank you for watching my lectures, okay. Share to your friends. Till now if you not subscribed, then compulsory you have to subscribe my channel to get updates and press the bell icon also. Thank you.